Assalamualaikum and good day. So today we're going to learn about about drain feedback biasing circuit continuations. Okay. So drain feedback biasing circuit. So when I told you when we have feedback means there is something from somewhere going back to somewhere. Okay, means there is connection from some part to another part. So that is what feedback normally, for example, some of the output going back to the input. Not necessarily input, sometimes in the middle point. It's just that feedback means something value that has been produced or something being feedback being used again. Okay. So in drain feedback bias circuit, when we want to solve, okay, is similar to maybe BJT. So, or we have two ways of solving it. Okay, so we have two methods, which is the graphical and the mathematicals. Okay, so for example, this question is asking to find IDQ, VGSQ, and VDSQ. So where is IDQ? Is ID. So ID is the current flowing through the terminal D, and then we have VGS, which is here actually, and then VDSQ. So since this is Q point, this one is actually the AC, it's actually the DC. It's actually the DC intersects with the AC. So we are solving for the DC now. So when we solving for the DC, practically we open the capacitors, okay, leaving only this structure. Okay. Then we're going to solve using two ways, whether graphical and mathematical. So before we solving that, we open, then we only left with this structure. And if you notice the RG, there is none of the RG here. Why? Because like we learned previously, in DC analysis, FET biasing general relationship, all FET. For all FET, IG is equals to 0. Meaning to say, ID is equals to IS. Okay? Not equally to 0, but approximate 0. Just like, for example, in the BJT, right, we have CBE, collector emitter approximately equal to IC. Why? Because IB is too small. And for enhancement type MOSFET, this is the formula. If you see this, means it's like there will be like a quadratic shape, because there is a of 2. Okay, so why we suddenly didn't have any more RG? We simplify the circuit is because IG is 0 ampere for all FET, the general. So if IG equals to 0, means there is no VRG. VRG is equals to 0 because if you IG times IG, okay, IG RG is the voltage here. Since IG is equals to 0, okay, so no matter what your value of RG, it will become 0. So that's why we no longer have a resistor here because VRG is equals to 0. Therefore, because of this situation, so your VDS, which is here, sorry. So your VDS here, so your VDS here is just equals as your VGS. Because there is no voltage drop here, so your VGS is equals to VDS. So if you make the equation for example, the equation here for this loop, example, so to make, for example, V, okay, we're going through here. Say we start from here lah. Okay, we start from here. So we this plus ground. So we start our loop here. So it's minus VDD. So we just rearrange. Okay, so no problem. IDRD. And then VDS plus VDS equals to 0. Since VDS is equals to VGS, so that's why we have VDD minus IDRD, and we replace VDS with VGS equals to 0. Okay, then we can rearrange again. So you will have VGS equals to VDD Is there something that I draw wrong? Oh, here, sorry. This one is negative. Huh? So VDD IDRD plus VDS. Okay. So I am using this loop. I am using this loop, for example. VGS equals to VDD minus IDRD. For one, VGS DD minus IDRD. So this one is going here. This one should be negative. Negative IDRD. And then this is minus VDD. Oh, okay. No wonder. Salah tanda. Sorry. I do the KVL. I do the looping wrong. Sorry. Okay. Looping is not wrong. The positive negative. No wonder lah macam pelik. Sekejap. Okay, sorry for that. Susah lah nak lukis macam ni. So if you nampak, if you see, okay, this one is positive negative. This one is positive negative, and then I took this loop. Okay, I took this loop, this direction of loops. Okay. So from here, let's say I start from here lah. Okay, so you have minus VDD. Okay, and then IDRD is in the same direction. IDRD. Okay, and then plus VDS equals to 0. Okay, since VDS ni is equals to your VGS, IDRD plus VGS equals to 0. Okay, then nak cari VGS, you just have to rearrange. So you're going to have VDD minus IDRD. IDRD. So ni baru betul lah. It's okay because we take here. Tapi kalau you ambil loop kat sini pun tak ada masalah. Okay, so be careful with positive negative. So first way to solve is by using graphical. So we go through the graphical first, and later we go to the calculation. Okay, so the graphical is like you do in other previous chapter, right? So you have this kind of graph for the DC for the AC. Okay? Then like using VGS is equals to VDD. So you're going to have the next intersection. And for this intersection, you know that ID, current passing through terminal D, is equals to VDD over RD. This figure, if you see from the figure given, there is no RS. Okay, there is no RS, only RD. So that's why we only consider ID RD lah. So ID equals to VDD over RD. In this situation, VGS is equals to 0. So ID equals to VDD over RD at VGS equals to 0. So you get this Y intersection. Then you can make your straight line. The intersection is the Q point. Okay. So IDQ and also VGSQ. In case just in case it is not the curve, which is this one, is not being given. Sometimes question can give you the curve, then you make the load line. Sometimes you need to do your own. Okay, so in case you need to do on your own, you need to plot the transfer curve. So VGS, the threshold voltage, where at that time there is no current passing through ID. So you can get this threshold voltage from the datasheet. The next one that you can get is the VGS on when the start of VGS on, when ID is on. So you can get this value as well on the specification sheet. Okay, so given that you have VGS on and ID on, so you can settle for your K, because K is what? K is ID on equals to VGS on. Remember I told you right in the previous class. Okay, K is on everything, and then you have VGS TH and then square. Okay. So using that from information on the datasheet, you can settle for your K. Okay. So this one has been touched. Intersect is the Q point. So using the value of ID at the Q point, ID or VGSQ depends, then we can solve other variable of interest by the questions. Okay. So next is the by calculation method. So we need first analyze the loop, the input loop. So if you notice, okay, I just look this. I don't. This one is the FET inside. Then we have DG terminal. Okay, DG terminal. I just look at this for simple looking. And then the input loop. So we need to analyze the input loop. Example, let's say we have depends if we have RS, means if we have a resistor at the inputs. Okay, and this is an input, right? Just like BJT, right? This one is our input region, and then this is our output. But also this one depends on your on the question as well. Okay, it's just generally this is your input. Okay, tak ada big button ke? Okay, so I have to use eraser. Okay, so continue. So first analyze the input loop. So input loop is actually your VG, minus GS and minus RS. So don't worry about this positivity. It's just that you do according to the to the looping. Just now, saya pun buat silap jadi kadang be careful sikit. So VG kita buat ikut loop. We start from here. For example, let's imagine just imagine lah, positive, negative VG. So is this in the opposite direction? You start from here, VG, and then you have plus GS. And then you have DRS. This one also depends, depends whether what kind of things that you get. Whether you get a D channel or you get a P channel. Okay, because there is difference in the direction of current. So, for example, if we just stick to this slide, okay, we go to the previous one first. We see what is the so going in. You see here, it's going in, going in. It's going in, so it's actually opposite direction lah. So, it's going in. Depends arrow masuk ke dalam ke keluar. So this one is here. Okay. So that's why you have this is opposite the loop with the loop direction. So it's minus equals to 0. Then we rearrange. So we get our VGS equals to VG plus IDRS. Again, it is depends. It depends on your channel, which channel that you get. So I am using the channel just now. Okay? I am using the channel just now. So minus VGA and plus VGS, which is here. And then I am using IDRS going up lah. Okay, because if you see previous slide. Where is it? Like for the P channel and channel. See here? So you have N channel. So where it is going inside. And you have channel where the arrow is going up. So it depends on what channel that you give lah. So I am using the N channel. N channel, the current flowing in. Regardless, just sure which one is P, which one is N, and the operation lah. Okay. Then to make the complete your KVL, okay, and then we insert the equation of your VGS. Okay, you put this equation inside here. Okay, you're going to solve for ID, okay, the current passing through the drain, and the and VGS. Okay, depends on the question. So if you see this one is quadratic equation. So what you learn from quadratic equation, you will have two values. Okay, only one is negative and one is positive. Okay, for the quadratic, but sometimes you can have two positive. Depends, depends. But you will have two values, right? So when you solve this, you're going to have two values. So if there is one value which is greater than threshold voltage, then that is your value of VGSQ. Then IDQ. So use the IDQ from calculation, from the calculation to calculate your VDSQ. So determine exercise. You can try at home and please try. Determine IDQ and VDSQ. If you notice, this value is given. So why this value is given? This value is given because it wants you to calculate the K first. K, which is ID on over VGS minus VGS on minus VGS H over square. So this one you are given ID, you given VGS on, you have VGS, so that you get the value of constant.